Okay, now we're getting into the meat of the unit. I feel like we had a lot of lead up to this lesson actually. So we're going to be factoring higher degree polynomials now. We're going to do lesson 5 and lesson 7. I think I'm going to roll and do both together. Maybe I'll post them separately. I'll post them separately. Okay, lesson 5. We're skipping lesson 6, by the way. It's only a extracurricular thing. So consider the polynomial x squared plus 4x plus 3, and it's shown over here. So if you have the graph of it, we can say things about this. We could write this in factored form as f of x equals, our first root is going to be minus 1, so it should be x plus 1. Has to be backwards in there, so if you subbed in -1, you get to 0. And the second one's at -3, so x plus 3. And that's pretty much it. You have your two factors, that makes your two roots. And you kind of have some a value. Well, the a is the same a as this one, so it's actually just 1. But sometimes you might have something here in the front. It might have some kind of coefficient, which stretches it. But the things in the brackets tell you where all the roots are. So the graph of this function has x-intercepts at -1 and -3. If you have the function and it's factored as it shows below, this has zeros of -1 and -3. It's the exact same thing. And if you set up the quadratic equation with it equal to 0, this has solutions of x could be -1 or x could be -3. So just reminding you that we have 3 different ways of saying the exact same thing. Each one kind of is tied to its situation. So solutions is often for an equation, zeros is for factored form, and x-intercepts is for the graph. These two are really kind of, they can be flip-flopped. But 3 different ways of saying the exact same thing. So we have all the language. Okay, the factors of a polynomial, x squared plus 5x minus 24, are what? Okay, so we need to add to 5, multiply to -24. So two numbers that are 5 apart. Let's see, I should get my calculator. It's going to be somewhere in the middle. 6, 12, 18, 24, so 6 and 4, but that's not going to work. 8, 16, 24, 8 and 3, that's going to be it. So +8, -3. Actually, the factors are x plus 8, x minus 3. That's right. State the zeros of this polynomial function, so either x is equal to -8 or x is equal to +3. What do you notice about the constant term? So now we're going to use the trick. We kind of showed in the last example, I know it was a while ago, how we could actually factor this whole thing if we knew one of the factors. So now we're trying to get to the trick to how to find the first factor. What do we notice about -24 and these two numbers we found? Or the two numbers we found here, either version of them, plus or minus. Well, they multiply to get to 24. What do you notice about the constant term and the zeros? The zeros multiply to the constant term. Or they're factors of the constant term. So they either multiply the constant term, or you could say they're factors of the constant term, which means they divide them evenly. So the factors of a polynomial, x cubed minus 2x squared minus x plus 2, are x minus 2, x minus 1, x plus 1. State the zeros. Well, from the first one, it could be +2. From the second one, it could be +1. And from the third one, it could be -1. So just taking all the numbers and flipping them the other way around, we've done this many times. What do you notice about the constant term of this polynomial? 2 is equal to 2 times 1 times -1. Except it's actually this version, right? -2 times -1 times +1. So the factors, the zeros, multiply to the constant term. Ignoring sign. Ignoring, if I can spell. So this is actually going to be true with every single polynomial because of the way we expand factors. If you have it in factored form, the way you expand it using FOIL or using advanced versions of FOIL, always these numbers at the end are going to multiply and they're going to turn into the constant term at the end. And that's going to be one of our big tricks. So integral zero theorem. The zeros of an integral polynomial function with a leading coefficient of 1, so just our simple ones so far, must be factors of the constant term. So if we have the following polynomial, the constant term is -6, this tells us that the zeros of it must come from the list. They must be either positive or -1, positive or -2, positive or -3, positive or -6. We can't tell exactly what the signs are going to be, and it's better not to kind of worry about that because it can very easily switch around. But those are the only 8 numbers you actually have to check to find out which one is a factor. And all the factors are going to be there, so it's actually going to be 3 numbers from that list. 3 different numbers that multiply to 6. So it could be 2 and 3 and 1, or it could be 6, 1 and 1, or I don't know. It could be, but it's very likely going to end up being 1. Anyway, consider this polynomial. List all the potential zeros. Well, it's positive or -1, positive or -2, positive or -3, positive or -6. These are our potential ones. List the potential factors. This means that you will be writing it in factored form. It might not contain all of these, but some of these will be factors. So I should put commas. This isn't actually factored form. This is just a list of possibles. So x plus or minus 1 could be one of the factors. X plus or minus 2, x plus or minus 3, and x plus or minus 6. So those are 8 different bracketed ones, and 3 of these are in our function. We just have to find out which ones. So identify one of the actual factors of the polynomial. So we're going to go back to the theorem we learned the other day. If you're a factor of a polynomial, if you sub in p of that number, then you should end up with 0. So we're going to check some numbers. P of 1 is probably the easiest one to check. So what is P of 1? You sub it into this question, you get 1 minus 7 minus 6 is not equal to 0. That's the only thing we care about. We don't care about the number it is. That one was -12, I think. But it wasn't 0, so we don't care. What about P of -1? So I sub in -1. Cubed is still -1. This becomes +7. So now I'm at +6. Subtract 6 is 0. So we got one. -1 is a factor of this polynomial, which means if you had to write in brackets, it's x plus 1 is one of our factors. So that's all you have to do. You could actually keep going and you could find the other factors. At this point, you kind of have 2 options. You could keep going and checking these other numbers, although when we get to more complicated polynomials, they might not all be integers. So you might not be able to find every single polynomial this way. So the alternative is we now want to do what we were doing before, which is synthetic division, and find what's left and then factor it. So we're going to pull out -1 and we're going to change its sign to +1. Is that right? Oh no, we keep the negative 1. Yeah, we switch the signs. And we write the polynomial down, so it's 1, then it's 0, don't forget to add the 0 in there, -7, and -6. Okay, so 1 becomes 1. 1 times -1 is -1. Add them together, you get -1. Switch to +1. You get -6 now, and you get +6. And when you add those together, you end up with 0. So nice and easy. So we know we can write this as x plus 1. And what's left is x squared minus x minus 6. Okay, then all we have to do is factor what's left. Now that it's a binomial, sorry, not binomial, now that it's a quadratic, a second degree function, we can factor it using our old methods. So that should be -3 and +2. X minus 3, x plus 2. Makes -6, adds to -1, yeah. And that's it. That's, of course, one of the simpler versions. We're going to get ones where they're not all whole numbers. But that's the idea. Okay. Consider the polynomial. So we got 4th degree one now. But it's going to be the same method. We're just going to have to do it a bit more. So this could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6. 12 is really, really annoying. There's actually a special term for some numbers like 12, which is called highly factorable or something. I forget what it's called. But basically there are some numbers that have an abnormally large number of factors, and 12 is like the first one of them. 24 is also, of course, a really, really factorable one as well. So if we want to be annoying on the test, we usually put a 12, because then it makes you check a lot of different things. Many numbers only have like 2 or 3 different factors. Express the polynomial in factored form. So we need to check some of these numbers. Let's check, what is it called, p? P of 1. Is that equal to 0? I didn't actually get my calculator last time. Well, that's 1 plus 2 is 3, minus 7 is -4, -12 plus 12 is 0. That's convenient. Yeah, so p of 1, boom, we've got one of the factors. So now we could already use synthetic division and turn this into a 3rd degree polynomial, or we could try to find another one. Let's try -1. Let's see if we can find another one. P of -1 is equal to 1 minus 2, -1, plus 7 is 6, minus 8 is -2, so nope, that one doesn't work. P of 2. I'll have to put this in my calculator. Actually, I've got the answer over here. This one does indeed work as well. This one is another one of our zeros. This was a simple polynomial, so it should have 4 of these 10 numbers. So it's not that uncommon to find a success. You might have to search for a while. Sometimes it's a bit annoying, but usually you can do it. And if I don't tell you have to show me your answers, you can use graphing calculator as well. That's the nice little trick. If you look on the graphing calculator and you find where it hits the x-axis, if you find one of the x-intercepts, boom, you found one of the factors. So it could be something really nice where one of them is a whole number and then the other 2 are decimals, and then that's perfect. Use the whole number as a factor, and then you can find what the decimal ones are after. So I've got 2 of them. So we're going to do synthetic division. 1, 2, -7, -8, +12. And I've got 1 first, so I'm going to put a negative 1 over here. Oh no, I want to use the right version of it. Sorry, I keep getting that backwards. It is the number that you sub in. It's the opposite of what's in the brackets that goes here. So it can be a little bit hard. We were going to write that as x minus 1. But we don't use the negative 1. We use the positive 1. So we use the number that we actually found. So the actual solution. Okay. So that's 1. Makes 1. Makes 3. Makes 3. Makes negative 4. Makes negative 4. Makes negative 12. Makes negative 12. Makes 0. Which is good. So we've got it factored the first time. And now we actually want to do this again. So we actually are going to be pulling out that factor, and we're going to be pulling out x minus 2 as a factor as well. So let's take our polynomial. This is our polynomial that's left, our third degree one, and let's actually do that again. And this time we're going to do it with the positive 2. So that's still 1, that becomes 2, that becomes 5, that becomes 10, that becomes 6, 2 is 12, is 0. Good. So we can write it as x minus 1, x minus 2, and the thing remaining is x squared plus 5x plus 6. Okay, let's find the two solutions that we didn't find before. Multiplies to 6, adds to 5 is 2 and 3. X plus 2 and x plus 3. Good. And that's it. That's all the hard work. State the zeros. So zeros are 1, plus and minus 2, and negative 3. So we got positive 1, positive 2, negative 2, and negative 3. 4 different zeros. State the roots of the quadratic equation. The same thing. X is kind of the group of, if we want to write it that way. X is the group of these numbers. It's the exact same answer. The zeros of the function are the roots of the equation. Okay, factor this polynomial. Then use the factors of the polynomial to express polynomial expression to determine the zeros of the polynomial function. Verify it using the graphing calculator. Okay, so factor it fully. Almost every time we say to factor something, we mean fully. So fully, you need to do everything. If you forget a common factor, that's actually the most common thing that people make as a mistake, is sometimes there's a common factor, they don't pull that out, and they end up with an answer like 2x plus 4, along with a whole bunch of other ones, which kind of, it looks like it's going to be fully factored, but you could have pulled a 2 out of there. That should have been x plus 2, and there should have been a 2 common factor at the front. And that's where you lose a half mark. So that's, be careful with the common factor fully. Be careful with the factor fully. Always look to common factor first. Okay. 2x squared. Do you guys have this one on your sheet? Oh, I'm just looking on your sheet now. You actually don't have this question, do you? You had this last one, though. Instead, you have x cubed minus 3x squared minus 3x. X cubed minus 3x squared minus 3x plus 1. Okay, we'll use your question. So we want to find the zeros to the nearest hundredth using your graphing calculator. So I think you guys are pretty good with this. You want to put this into your graphing calculator, solve for the zeros, Same thing you did with your quadratics. And you should find the answers are -1, 0.27, and 3.73. So make sure you actually try that one. It shouldn't be too hard though. It's basically the exact same method as the quadratic that we did in quadratics. So we have one really nice one and we have two bad ones. Now this wants us to find the exact values for these bad ones. You could kind of write it, if you wanted to write it in factored form, you could write x plus 1, x minus 0.27, dot, dot, dot. But that's not factored. Factored, we don't like to have decimals. We don't like to have real numbers. We always like to have everything as integers. So that's not actually factored form, even though it's mathematically true. So we're going to do this the right way. So we know that x plus 1 is one of our factors. We're going to find the rest. So we're going to use the -1, and we're going to use 1, -3, -3, 1. And we're going to find out what we left behind. So 1 is just 1, becomes -1, -4, becomes +4, becomes +1, becomes -1, becomes 0. So that was indeed one of our factors. The calculator didn't round on us. It was exactly -1 is one of our solutions. So the remaining polynomial is x squared minus 4x plus 1. And now we need to find the solutions to this. And you could try to factor it, a number that adds to -4 and multiplies to +1, but you're not going to be able to find it. It's not an easy number to get to. It's not an easy fraction or an easy integer, of course. So what we're going to do instead is the quadratic formula. X is equal to negative b, which is 4, plus and minus root b squared, 4 squared. I leave off the negative there because you're going to square it anyway, so I actually always kind of just ignore the negative. If you do put the negative, make sure it's kind of in brackets, it's under the square, otherwise you can mess up your answer. Minus 4 times a times c all over 2 times a, which is just 2. So, quadratic formula, and you're going to get this down to x equals 4 plus or minus root 12 all over 2. And then this simplifies. That step should be easy. Now you want to rewrite root 12 as it divides by 4, so it should be 2 root 3. Is the one thing you're going to do at this step. And then you're going to divide the front and divide the back. So when you divide the front, it becomes 2. When you divide the back, it becomes just root 3, because the 2 divides by the 2. Always divide the coefficient. 2 plus root 3 and 2 minus root 3. And those are our two exact solutions for this one. So this is a throwback to what I was doing with the grade 11s. So hopefully we remember how to simplify our roots a bit and how to get a quadratic formula into exact answers. You do quite a bit of that in grade 11, so hopefully that's familiar. Okay, that's it for this one. The only thing we have to do now is when we have a bit more complicated polynomials, how do we find that? But really it's actually going to be very similar to this method. You got to find your one answer, then you got to get what you have left, and then you got to find some way to get to your other answer. It could be a decomposition factoring, or it could be the quadratic formula, or something like that. And that was it for that one. Did I have this question? Yeah, we had this question anyway. It was down there. We could look at these other ones, but I think they're fairly straightforward. Okay, 25-minute lesson this time, and then I'm going to go right into lesson 7. It's pretty short too.